Welcome to Phase 3. You've built meshes, set physics, and understood the solver. Now we point all of it at real problems. First up, the one that pays the bills in aerospace and automotive: flow around a body. External aerodynamics is flow over the outside of an object, a wing, a car, a building. The goal is almost always the same: the forces the object feels. Drag and lift. The first mental shift. Until now, our flow was internal, inside a cavity, inside a channel. External flow is the opposite: the fluid is everywhere, and the object is a hole in the middle of it. Internal, the mesh fills the container, and the walls are the geometry. Familiar from the cavity. External, the mesh fills a big region of open air, and the body is cut out of the middle. Most of your cells are just surrounding fluid. That changes how you build the whole case. So how much empty air do you mesh around the body? Get this wrong and your answer is quietly, confidently incorrect. Too small, and the outer boundaries sit right on top of the body. They squeeze the flow like walls in a wind tunnel that's too narrow, an effect called blockage, and your drag comes out too high. The fix is simple: give it room. A rule of thumb is 10 to 20 body lengths in every direction, and even more downstream, because the wake needs space to develop before it hits the outlet. The outer boundaries need conditions too, and they follow the inlet-outlet logic from episode 4, just spread around a big open box. Upstream is the inlet, the freestream velocity flowing in. Downstream is the outlet, fixed pressure, letting the wake leave. Same seesaw as before. The top and bottom get a slip or freestream condition. The flow slides along them as if they weren't there, since they're really just the edge of our simulated air. And the body itself is a no-slip wall. That's where drag is born. You don't mesh all that open air evenly, that would be a waste. Straight from the grading lesson in episode 3, cluster cells where the flow is interesting. Refine a region hugging the body, that's where the boundary layer lives and where drag is set. Remember Y+ from last episode: those near-wall cells decide whether your drag is trustworthy. And refine the wake, the disturbed region trailing behind. Coarse cells there smear out the very vortices you often care about. Everywhere else, big cheap cells are fine. Now the beautiful part. Run flow past a cylinder above a certain speed, and it does something remarkable: it sheds vortices, alternately, off each side. The wake becomes a staggered street of spinning vortices, the famous von Karman Vortex street. One sheds from the top, then one from the bottom, over and over, in a steady rhythm. This is inherently unsteady, so you'd solve it with pimpleFoam from episode 9, and likely a turbulence model from episode 10. Everything we've built comes together in this one iconic flow. And it's not just pretty: the shedding frequency is a real, measurable engineering number, captured by the Strouhal number. Get it wrong on a bridge or a chimney, and resonance can destroy the structure. Finally, the whole point: the forces. And thanks to episode 7, you already know the tool, a functionObject that computes them while the run goes. Add a theforceCoeffs object pointed at the body patch, give it the freestream density and speed and a reference area, and OpenFOAM integrates the pressure and shear over the surface every step. Out come the drag and lift coefficients, CD and CL, written straight to file as the simulation runs. Those are the numbers an aerodynamicist actually reports. No hand calculation, no guesswork. That's external aerodynamics. A roomy domain of open air, far-field conditions on the edges, cells clustered on the body and wake, and theforceCoeffs handing you drag and lift. Every piece of the series working together on a real problem. We can find the forces on a body. But real engineering often cares about heat too: a hot component cooled by airflow, or solid and fluid exchange energy across their shared surface. Next episode: conjugate heat transfer. See you there.